this integrand. Okay, so what is composite trapezoidal rule? Okay, so in your calculator and computers, the method that is implemented based on trapezoidal is composite trapezoidal. Keep in mind, because composite is is the same as trapezoid, but it gives much better result in accuracy. How? You will understand very easily. So composite trapo trapezoidal rule. So point that why I'm giving so much time to it is because students are confused. They think that trapezoidal rule is different thing and composite trapezoidal rule is different thing. Now you will understand why the word composition or composite is added in it. The student idea is quite simple. We have a problem that we want to replace our integrand a to b f of x, which is very difficult to solve, by a polynomial of degree 1. Whenever you say degree 1 means you are talking about trapezoidal rule. But the problem is usually f of x is not a straight line, it is a curve, and we cannot approximate a curve by a straight line. For example, f of x is defined like that, and what we are trying to do, we are putting a straight line over it and saying that okay, this straight line represents this solid curve, white curve, which is obviously not possible. But what we can do one thing. If this curve is so big, like starting from there and ending it there, so it has a proper curve in it. What can we do? Rather than using a complete set of a curve from A to B, we can divide that curve into a small pieces. Okay, so we can divide that curve into a small pieces, and once we divide that curve, then what can we do? We can apply a trapezoidal rule on each piece. For example, rather than reflecting this whole curve from there to there by a one straight line, I can do one thing more. If I divided them in a small pieces, that's called composite. So if I divide into a small pieces, then I can do one thing. I can draw a straight line between these 2 points only, and I can draw a straight line between these 2 points. It is a different straight line, but I can draw it. Similarly, I can draw a straight line between these 2 points. I can draw a straight line between these 2 points. I can draw a straight line between these 2 points, and so on. So what I'm doing, I still have a one curve, but I divide it into a small pieces, and when they are in a small pieces, so what I'm doing, I am constructing. This is what I'm doing. So I'm representing the small piece of my curve by a still a straight line, that is a polynomial of degree 1. But rather than using a one line like this one, I am making this interval to be represented by a small line. Why I am doing this? That's the main point. Since we all know that if the curve is larger, we cannot reflect it by a straight line because there is always an error. But if we make it very small, then it could be represented to certain extent by a straight line, because once the curve is very small, the small element, it behave like a straight line. It could not, it is not possible that it is exactly represented as straight line, but it could be a very small. So if you have a curve surface and very large, so you cannot represent it by a straight line because this will. But if you make that curve very small, then this portion can be represented to certain extent by a straight line. So this strategy to enhance the accuracy is called trapezoid rule. And why I'm calling it trapezoid, because you remember I said I'm replacing each interval by a straight line. Straight line means polynomial of degree 1. So whenever we replace our integrand, whether completely or a small portion, so technically we are talking about a trapezoidal rule. Now question is, how do we achieve this thing? This is just for an idea. So how do we achieve this thing? It is very simple. How do exactly we do this? So student, idea is quite simple. Keep in mind, still it is still a trapezoidal rule. I'm repeating it again and again, but we need to enhance the accuracy. So to enhance the accuracy, the strategy is, rather than applying it on a one curve to the whole integrand, let's divide it into a small pieces and apply trapezoidal rule in each interval, so that you will get a better curve. And how I can get a better result? Because in a small segments you can represent a curve surface by a straight line to certain extent. Or obviously it is not going to be exact but certain. So let me explain you geometrically how we will do that. In fact, I will draw it here, then I will write down something on this part. So an idea is still the same. This is x and this is y. Origin. The first value is a and the last value is b, upper limit and lower limit, and then you have a some function integrand. So it is plotted like that. Okay. So this is your integrand. That is y equal to f of x. Again, we cannot solve integrand, but we can plot it. It is just a function. So, and our target is to compute the area under this curve to as much as accurate is possible and above this x-axis. So what we did, we want to apply trapezide. When we want to apply trapezide, we will replace it by a straight line. But we know that if we replace a straight line one time in a big interval, we will get much more error. So strategy is to divide that curve into a small pieces and then apply a trapezoid rule on each piece, so that you will get an area under that piece, and then you add up all the pieces, you will get the total area. So, but how we will do that? It is very simple, but we have to define some convention there. Understand? The limit here is of for x values. It is moving from a to b. We all know that limit is ranging from a to b. This is lower and this is upper value. So integral that I want to perform is moving from a to b. Here are many x values. Okay. So what we will do, we divide that interval from there to there into a small pieces of equal length. For example, I will divide it like that. I select one point here, 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 and so on till there is some second last point. How we will do that? Very simple. So what I did, I said, okay, the first point is A and the last point is B. So I have to, because I am not only relying on only 2 points, A and B, I have divided that interval from A to B into a small pieces. A, this point, then this point, then this point, then this point, and this point. It's just like the data that we have represented in the operators as well. So when we divide, we have to label them. So how we can label them? Let's say this interval is from A to B, and I have divided into n intervals. Okay, so n intervals. So this means that the length of each interval, this is the one interval, the length of each interval is calculated by this formula. B minus A, this is the total length from there to there, and if I divide it into n pieces, small n pieces, so let's say I divide it into a small n piece, or let's use the capital N symbol. I divide it into n pieces, so this will give me a length of each interval. So length of each interval is h. There is one interval from A to B, and I divided that interval to a small pieces, so this length from there to there is h. Now from there to there, this is also h, and now from there to there, this is also h, and so on. Similarly till last point, this is also h. So all intervals have a length equal to h. I divide my domain of integral from A to B into a small pieces of my choice. I can set n20, I can set n30, n40. Whatever I will do, I can do it. But there is one inference that we have to make sure, that if I increase n, that is n represents what n represent? N represent number of intervals. It is just a count. 20 intervals, 30 intervals, number of intervals. And intervals is this quantity. From there to there, there is one interval. From there to there, this second interval. From there to there is the third interval, and fourth interval, and so on. We will reach to till B. We will not go more than B or ahead of A. So B minus A, n is the number of interval. But we know that if n goes to very large, and mathematically when we say it goes to very large, we want to say n tends to infinity. If n goes to infinity, student, we can clearly see that that these points are not moving ahead of it. They have become very close to each other. They will move very close to each other. Okay, because if we make n larger, this h will decrease. If n tends to infinity, that is n become very larger, then h, that is the width of the interval, goes to 0. This is width of the interval. That is how much width of interval. Width of interval, that goes to 0. Okay, so this is what you have to add. So this is n, we select ourselves. It is not given to us, we will select it ourselves. Interval, number of intervals. So this gives h. Now what we will do, if I add, this is a, the starting point, and if I add, if I am, let's say I'm here and I am at a, and if I add h in it, so I will get a plus h. A plus h is definitely at this point, and if I add again h in it, I will reach there, and if I add again h, I will reach there, and if I add h again, I will reach there, and similarly if I add h there, I will reach to the last point of this data. So this means that by adding h, we can generate the coordinates of these points as well. Okay, so rather than generating them, let's call them, label them. So how I can label them is like that. The first point in our data, I will label it as x naught. I call it x naught. Okay. The second data is this one. I call it x1. Similarly, the third point in the data, I call it x3, x2, and similarly, we will continue and we will reach to a somewhere in the last point, and I will label that last point is xn minus 1, and the last point in our data is labeled as xn. Now question is, how we are so sure that we will get the last index is xn, because this capital N is same as this interval. So student, we have to recall a very simple concept. If we have a three intervals, then which means that I have 4 points. What does this mean? For example, I have three intervals of a data. So this is interval number 1, this is interval number 2, this is interval number 3. So I have three intervals. So here n is 3. So how many points I have? And we call it nodes as well. How many nodes I have? I have node 1, this is node 1, this is node 2, this is node 3, and this is node 4. So if I have n intervals, that is 3 intervals, I will have 4 nodes. 4 nodes. Nodes means points, x coordinate. 4 nodes. So can you generalize it? For example, if I ask you, if I have 5 intervals, that is n is 5. So how many intervals, how many nodes I have? So we have a relation. Relation says that whatever the number of intervals you have, you will get one more nodes. So here we have 3 intervals, I will get 4 nodes. So similarly, if I have a 5 intervals, I will get 6 nodes. So now question is, if I have n nodes, I said I will use n nodes. Then how many points I have? I will have n plus 1 points. How many points I have? N plus 1 points. So if, let me write down, if n intervals, we get n plus 1 points. So the question is, then is the label is correct? The first point I label, which is the lower limit as well, I call it x naught. The other point which will be generated by adding h in the a is x1, x2, and the second last point is xn minus 1 subscript. They all are in subscript. And the last point is xn. xn. Is it correct? Then the label of the last index is xn. Yes, it is correct. Why? Because I told you there are n intervals. So the total points, that is from there 1, 2, 3, 4. Total point would be n plus 1. So I started labeling from 0. So if I start labeling from x naught, then last point must be xn. Because if I started from 1 here, from x1, then the last point must be n plus 1. But I started from 0, x naught. So this means that the last point is n, xn. Okay. So do not confuse it like that. Okay. So how we will handle this thing. So the first point is x0, the other point is x1, and so on. It is just like something we discuss in a difference equation data as well. So, but these are the x values, not y. So similarly, if this is x0, then I will get y value as well, and this y value is called y0. How will I will obtain this y value, this height? Very simple. I will put x0 in this function, and I will get y0. Similarly, if this is x1, which is known to me, so I can put x1 in this function, that is integrand. I will get the height, and that height is y1. Similarly, I will put 2 here, so I will get the height or and this interval as well. And if I continue like that, so I will reach to a some second last point as well. Let's draw second last here, not here. So this second last point will have a, because the second last point has a coordinate xn minus 1 subscript, so this means that the sy height would be yn minus 1 subscript. And similarly, this is the last value, which is the upper limit as well, b, and b is represented in our label as xn. So the last node, which is this node, is y capital N. Okay, so these are the label, and this is dotted, means number of points can be in between them. So we can continue similarly like that. So this is, so the idea is, rather than replacing your integrand, this is the complete integrand, and you want to find the area beneath this. So rather than replacing it by a single straight line, you will generate much error. It is better to divide the interval into a small segments and replace each segment by a straight line. Okay, in other words, apply a trapezoid rule in each segment. So let me use a different color, in fact. So let's use again a black color. So this black color represent application of trapezoidal rule in an individual curve. Okay, so you can see there are different lines, and similarly till the last part. So you can see that rather than fitting a one straight line, we will generate much error. But what we did, if we repeat this process in a small segments, so we have generated errorless. You can see that black and white are matching to certain extent much better. Although there is some error as well, but that error is much smaller than the amount of error we have. But if you want to increase the error, what can we do? We can increase number of intervals, because if we increase number of intervals, h decreases, which means that this point, which is situated at distance h, will move closer to that point. So we will have a y1 somewhere there. So interval is much better reflected. So we can increase the data set. But when we increase, and keep in mind, number of data points will increase as well. Okay, so this is one of the reason we do not do this, but this is how we have. So if we continue this thing, we will reach to the last interval, and in last interval we will have a same representation. Okay, so rather than applying a trapezoid in a one go, we will applying trapezoid in the form of intervals. So x0 to x1, x1 to x2. This is similarly in the last interval xn minus 1 to xn. And what we do, we will not compute the area, we will compute area of the individual segment. So the, let's say the first segment has the area a1, the second segment has the area a2, and we will continue, and the last segment has the area an minus 1. Okay, an. So this is how we generate the our interval. So if I will get this area, which is a1, and I will get this area, which is a2, and similarly I will continue with intervals, and then we will reach to the last element, last interval, and we will get this area. So if I add all these areas, so it will be representing the area beneath this curve, which much more accuracy, rather than just fitting a one straight line, which will give them much more error. Okay, so this will give much better. So this strategy, what I have done here, this strategy is called composition. So you have a one interval, and you divide into interval to form a composition, and then you are saying the area is totally represented by. So how we will get the formula is very simple. So I'm writing it with black color here, which means that I'm performing the color. So the final answer will have a area, sorry, equal to the sum of, final answer will equal to the area of a1 plus a2 plus A3 plus till whatever be the last area we can compute. Okay, so this is the answer, this would be the answer. Now question is, how do we compute a1, a2, a3? We have to compute applying the trapezoidal rule. So we know that if if we are only focusing on this curve, this interval, so we know that all of the lines are parallel lines are separated by the amount h, and the parallel sides has a length equal to y naught. Here the parallel side has a length equal to y naught and y1, and they are separated by a h distance. Similarly, for interval 2, the parallel sides has a length y1 and y2, and they are separated a distance h. Similarly, if we continue, we will reach to the last interval where they are separated still by a distance h, and the heights are yn minus 1 and yn. So we can apply a trapezoidal rule individually in each interval to get a1, a2, a3, and till an, and then we sum up all them, so we'll get the total area under this white curve with much better strategy. So that is called composition. So I am writing that thing in the next slide to conclude this topic, because at the end you have to memorize the formula. So A1. So the A1 in this case of a trapezoidal rule, f of x dx a to b is approximately equal to A1. Now I have to compute A1. So let me go back. A1. A1 is this area. So parallel sides are y0, y1 divided by 2 because it is a trapezoid rule, and they are separated at a distance of h. All of them are at a distance. So I am applying trapezoid but in a composite sense, in a smaller in each segment. So I will get y0 plus y1 divided by 2 sum of parallel sides average multiply by separation between them. So separation between each side is h distance. They are situated at distance away. This is A1. Similarly, I need to compute A2. I can do it directly. The second interval starts at y1 and at y2 length parallel sides divide by 2, and they are multiplying still by a distance h because that is equidistance. Similarly, third interval, which is not shown in the diagram, but if it's possible, it will end at y2, then it will start at y2, y3 divided by 2 multiply by h, and so on. And the last interval that we have is yn minus 1 plus yn divided by 2, and this whole also multiply by h. Okay, idea is whenever the one side ends, the other interval starts from the other side. So if we go back, because this is the common node, this height is common, this is also a part of this interval, and this is also a part of this interval. So this common nodes are appearing twice, keep in mind this. So this is the part, and if we simplify it, we because h is constant, so we can take out h, and we can see that all the terms as a denominator are also constant too, so we can take out 2 as well. So whatever left is inside is h upon 2 is taken out as a common, and we will left y0 plus y1, and this will also left, we will get y1 left over here and y1 here as well. So that will become y1 plus y1, that is 2 times of y1. Keep in mind h by 2 is taken out as a common. So y1 plus y1 is 2 times. So I will get 2 times of y1. Similarly, I will get y2 plus y2, 2 times of y2. All internal nodes will be multiplied twice in short. Continue till this is the first node of the last interval, and before that there also exists yn minus 1. So this will be 2 times of yn minus 1 as well, and the last interval is not multiplying twice because last interval is last node. It is not counting as a twice. Why? Let me show you from geometry. Last value and the first value is only counting one time. There is nothing interval before it and there is no interval after it. So these last nodes will be counting only one time, and all other internal heights will be counted twice. Okay, and this is the yn minus 1, and obviously there is some interval which is common by these two nodes. So this is the formula for your trapezoidal rule. If you want to apply trapezoidal rule in a composite sense, you have to do it like that. This is trapezoidal rule in composite sen. In short, this is a composite trapezoidal. So what does composite mean, sir? Composition means we want to enhance the accuracy using a trapezoidal rule. What do you mean by that? I want to divide the interval into a small segments, and each segment I will apply a trapezoidal rule. That is, I will replace the integrand in that segment by a straight line, and then I will try to find the area using a trapezoidal rule, and then I will add all the individual areas, because if you remember, this is A1, I added to, this is A2, and I will add till last AN. So I will get the total area beneath this white curve. This is called composition. Point that you have to note in mind that if N goes large, H tends to 0. Separation between the points goes to 0, means you have a very large points. Accuracy of this method, that is how much accurate this method would be, goes up. It become much more accurate. Keep in mind. But when you have a large N, means you have a very large points, and that point will cause a problem. Okay. So here I would like to end the lecture. In the next lecture, I will explain the other two methods as well, and I will not go too much detail in the other two methods. In this case, I will just explain the main point, that how the composition of the other method has been developed and what's the reason behind it. But this is the main theme. So just to summarize it, in numerical integration, we replace our integrand by a polynomial of suitable degree. Okay, this is the main thing. But in trapezoidal rule, we will select a polynomial of degree 1. And once we have a polynomial degree 1, we will get this composition, this formula of trapezoid. But that formula will generate an error. So to minimize the error, we will have another approach which will call composition. Composition approach is same as the trapezoidal rule, but it will enhance the error, decrease the error for us. What we do, we apply the trapezoidal rule in intervals, and when we apply the trapezoidal rule in intervals, we will have this formula. This is the formula that you have to know. This is the composition formula, and this is the formula which is implemented in your calculators as well, if you want, because in calculator you provide your integrand and your upper and lower limit. It will give you the final answer. It will select H and N automatically, and will generate this formula for trapezoidal rule if it is solving using trapezoidal rule. But there are other methods as well. Okay, student. So it is around 90 minutes or something, a little bit above, which is allowed. So thank you for your time. Go through this lecture, and we will discuss this on the 15th of July 2020. Again, thank you for your time.